And thank you, Eric, for that presentation. Really impressive. I'm glad to work with you. So hello, everyone. I'm Fredrik Olsson from Follou Haptics in Sweden. And I'm mostly going to talk about our force feedback hardware. So I chose this background to emphasize that this presentation is about hardware and in fact, a gear, not very different from what you see here, only much smaller, plays a very central role in what we are doing, strangely enough. So we have developed a system we call Haptic Avatar, which is mainly intended to be used for laparoscopic training simulations, but it's not limited to that. It can be used, for instance, for arthroscopic simulations too, or any other simulation where you have an instrument that is essentially suspended in a pivot point. So we do the force feedback hardware, not the entire simulation or simulator, but we aim to develop an example or a demonstrator using SOFA, and we are getting help from Infinitec and parts of INRIA team to do that. Anyways, I'm going to show you an example of a simple haptic avatar setup and explain the components in it, and perhaps you can see it right here next to me in the background. I'm also going to talk about how the 5 degrees of freedom force feedback is intended to be utilized in SOFA. So here we have a workstation that is built with the haptic avatar components. We have 3 force feedback devices mounted on a frame. We have a set of instruments which are placed on an instrument stand. And we have an instrument box, or in short, we call it an iBox. The workstation structure, the frame, consists of 3 rigid plates and a couple of aluminum structures. There is a bottom plate, a middle plate on which the haptic devices are fitted on quick connector plates, and finally a top plate for a laptop or an iPad. The footprint for the workstation is 25 by 40 centimeters, and the instrument stand has the same dimensions, so they are pretty small. So here's a close-up on the workstation, and you can see that the haptic devices are placed only 60 millimeters apart in a triangle that is common for laparoscopic procedures. You can put these devices as close as 50 millimeter without mechanical interference. The haptic device has sensing and force feedback in all 4 degrees of freedom, and it has a quite wide range in yaw and pitch, plus minus 90 degrees and plus minus 60 degrees, as you can see here in the picture. The specifications for the haptic device, I'm not going to go into details about them, but they're quite good in terms of strength, resolution, rigidness, inertia, backlash, etc. So it has the potential to deliver high performance haptics. From a usage perspective, the most important feature is that the instruments can be removed from the haptic device. This means that you can insert many types of instruments. And when an instrument is inserted in the haptic device, the tip of the shaft of that instrument will be identified by the haptic device. So the system will know which instrument has been inserted. This solution is intended to provide a more realistic user experience when performing a task or a procedure with many different tools. There are mechanical return springs in yaw and pitch, so the insertion part is pointing up when no instrument is in it. This makes the insertion of an instrument quite easy then. The calibration of the positioning is also a very important usage feature. It's very simple, and it happens when the 0 angle on yaw and pitch is crossed. And this is made only once after the device has been powered up. So this is nothing you need to do between every procedure or task or so. You can just rely on that calibration to be valid. So here you can see all the currently existing instruments that we have for this haptic device. In the lower left corner, we have a grasper type instrument, which can be used to represent a forceps, a scissor, a dissector, or the like. It has a sensor for opening angle of the thumb grip. And this handle has force feedback, which means that you can send forces to it and feel a resistance. And the motors are controlled and stabilized by the iBox. And we have an update frequency of 10 kilohertz to do this. The grasper type handle is also available without force feedback. So this is optional, the motor here. Over to the top left corner, we have a clip applier, which may be used to represent a stapler as well. Although the stapler is quite complicated instrument. This instrument has a lever inside instead of a thumb grip, and like the grasper, it also has force feedback, and you can send forces to it. And here you can also send a program, a force profile that mimics the application of a clip or a staple. So in the top right, we have a needle driver, also with a grip lever that you can manipulate. When the grip is fully closed of this instrument, it locks to that position. And to release the lever, you press a release button. And below the needle driver, we have a generic straight tool with 2 push buttons, which can be used to represent suction irrigation instrument, a spray applier, or a monopolar diathermy hook, etc. And finally, in the lower right corner, we have a scope. This instrument has an absolute angular sensor between the camera and the scope, which means that the user can train on camera horizoning and handling of angled scopes. It also has 3 generic push buttons and a zoom knob, as you can see. I mentioned the iBox, and here we have a close-up of the iBox. And up to 6 handles can be connected to it, and 4 of them can have force feedback. And I also have a picture of the shafts. And one important aspect for the modularity of the instruments is that the shaft is detachable from the handle. On the picture of the handle, you can see a gray button, and if you press it, you release the shaft from the handle. If a handle is connected to, say, a red shaft, the handle needs to be connected electrically also to the red contact on the iBox. This means that when the haptic device detects a red shaft, the software API knows which iBox channel to read the signals from and send forces to. Also, since the shafts are detachable, you can choose different shaft lengths and still keep the same handles. A standard shaft length is 310 millimeters, but it can be customized to be longer or shorter. And this picture shows a close-up of an instrument stand. And in this case, we have set up 7 instruments. And next, I'm going to talk about the sofa plugin that we are currently developing. And as I mentioned, we are getting help from Infinitec 3D and parts of the Enria team too to develop it. We have 4 degrees of freedom in the haptic device, and we have an extra degree of freedom in the handle. And I'm going to explain very briefly how to utilize them. So this slide shows a very rough schematic of the sofa plugin. So we have the sofa physics engine in light blue, and then we have a Haptic avatar plugin which implements the 1 kHz loop with collision detection and force generation. And these forces are sent to an API which hides much of the boring stuff like device connection, communication, and device status supervision, etc. But it also takes care of some of the fun stuff, like decomposing of the collision forces into demand torques to the motors, both for the haptic devices and for the handles. So in this slide, we see a simple collision force situation. The shaft collides with the liver, and the jaws is about to take a grip on the gallbladder. So we have 3 forces and their respective acting points. That is where their forces originate from. And these forces are now recalculated as if they were acting on the distal end of the instrument center line, and then they are summed. So now we can calculate yaw, pitch, and C torque on the haptic device. And by projecting the actual acting points on the center line and crossing them with the respective forces and accumulating them, the final torque around the shaft can be calculated to send to the haptic device. So now everything is ready for the haptic device, but yet not for the handle. The forces that acts on the jaws are now crossed with the acting points with respect to the yaw hinge. I see that my time is out here, so I'm going to skip this slide. Here you can see what information need to pass from the plugin to the API, and you need to pass the forces, the positions, which tool and which tool part that you collide with, and then you can get access to all the 5 degrees of freedom. As a summary, Haptic Avatar is a high-performance, flexible, and modular system, and it allows you to create a setup for many realistic scenarios and procedures. And a sofa plugin is underway, which is intended to demonstrate the combination of sofa physics and this haptic. And we hope to be able to demonstrate this live at the Sofa Week 2021. I think haptics is best sensed in real life.
Yeah.
Yeah.
Thank you. Thank you very much, Fredrik. Thank you very much. Nice presentation. Indeed, a lot of things and an interesting coupling between your innovative haptic devices and simulation. So François, François congratulates you, but if François or anyone else, I'm thinking also about Remy, or because there is a lot of projects that are going on that sometimes involve haptics, or at least devices that are communicating with the simulation. So we have just a few time for questions, and then there will be the break. So again, time for getting directly in touch with Fredrik. I see Clément from CAE who is starting to type up. I can't see the message. Perfect. So very interesting device. Design is surprisingly compact, and indeed, for having seen the devices last year, and it looks. It looks, but it is definitely extremely compact. Could you precise the amount of forces, the maximum forces you can actually get for each axis?
Yes, in the C-axis, that is the insertion, you can get 20 newtons. And in the yaw and pitch, you get around 0.7 Newton meters. And the rotation, I don't have it in my head, but it's sufficient for the rotation force feedback. You can absolutely, for instance, simulate a screw or so.
All your instruments are wired. Could it be could the wire be removed if we don't want force feedback on the handle?
Yeah, it can absolutely be that. And you can, for instance, have a Bluetooth connection. I think the problem is then from a user perspective, because if you have Bluetooth handles that needs to be charged, and if we think about a training situation and a training institute, for instance, which have, say, 5-10 training simulators, and all of these handles they communicate with Bluetooth, then there has to be a technical assistant there all the time to just resolve Bluetooth issues. But perhaps there are other ways to do it. I haven't looked into it very much.
So I can feel there will be additional questions. It's going to be the opportunity actually to take most of Fredrik who is here. I see that Jenny is also here. So we'll create, hi Jenny. I did not see you in the back of the room. You can actually, put full screen the view of Fredrik, and you will see in the background the Haptic device running. I think there could be possible demo also in this breakout room, so do not hesitate. Mm-hmm. For your information, for those who just joined for the afternoon, all the session will be recorded, and I'm thinking about Professor Choi from this morning, presenting a simulation about arthroscopy. He was also interested in laparoscopy, so I think he'll be super interested to afterwards, because it's already night for them in Korea, but they will be super curious and interested to have a look to your devices. So what I suggest is that we'll move to the breakout rooms. As you can notice, Guillaume already informed us. Room 1, Sylvain will ask you to join the room 1 for taking the questions. The same for room 2 for taking questions for Eric, and Fredrik and Jenny, do not hesitate to join the room 3 so that you can take all the questions. Guys, I'll let you go in the breakout rooms.